The first thing we want to go over is interval notation. Interval notation is a way for us to write our answer sets. It might be easier for us to graph our solution first and then write our answer in interval notation. Once we get into interval notation, you'll understand why we have changed some of the things with how we graph our answers on the number line. Our solid dots will be replaced with a square bracket, and our open circles will be replaced with a rounded parenthesis. Here we see a set of graphed solutions. Let's try and put these into interval notation. When we read our graphs from left to right, and that way we can get it into interval notation. When we're reading the number line left to right, we mention the first number that was shaded, which is a -3, and the last number that was shaded, which is a +5. Now a parenthesis on the -3 and a square bracket on the 5. Remember that the rounded parenthesis is the same as an open circle, and the square bracket is the same as a filled in dot. So this means that our solution set are all the numbers between -3 and 5, not including -3 since it's open, but including 5. Reading this graph from left to right, we see the first number that is shaded is a 5. And the last number shaded, well, it keeps going to infinity. So we have an infinity symbol that we use. And here we'll put a parenthesis on the 5 since there's a parenthesis in the graph. Reading this from left to right, we have the -3 is the first number shaded, and it keeps going to infinity. And yes, while this does go through the number 5, we don't need to mention it. It's no more special than any of the other numbers that we're going through. In reading this graph from left to right, we're coming from -infinity. So we simply write a negative in front of our infinity, and the last number shaded is the -3. Parenthesis on the -3 and always parentheses on our infinity symbols. Here we have from left to right, coming from -infinity and going to -3, square bracket on the -3 and always parentheses on infinities. And then we have a space where there are no solutions, and then we pick back up at 5 and go to infinity. What you'll want to do is put what we call a union symbol, and it looks like a U without the little tail. And we'll study more about that in a little bit. And that would be the way we would write that solution set. Now that we know something about interval notation, let's look at compound inequalities. A compound inequality consists of two inequalities joined by words and or. It may also be a three-part inequality. Here are some examples of compound inequalities. X is greater than or equal to 5 and x is less than or equal to 12. X is greater than 3 or x is less than or equal to -4. And 5 is less than or equal to x is less than or equal to 12. Now a solution to a compound inequality containing the word and must make both inequalities in the statement true. In other words, a solution must make the first part and the second part of the inequality true at the same time. So if we're looking at this compound inequality with the and, we have to pick numbers that would make this true and this true. A number that would make this true would be the number 7, because 7 is greater than or equal to 5 and 7 is less than or equal to 12. Now a solution to a compound inequality containing the word or must make one or the other or both inequalities in the statement true. In other words, at least one part of the inequality true. So when I'm looking at a compound inequality like this with the word or, the number 5 is a possible solution because 5 is greater than 3 is true, or 5 is less than equal to negative 4 is not true, but at least it made one part of that inequality true. This type of inequality is going to be the same as an AND statement. We'll see that later on in our lesson. Now determine whether the given values of x are solutions to the compound inequality. Let's try the number 2 first. 2 minus 1 is less than 5, and 2 times 2 is greater than 3. So 2 minus 1 is 1, is less than 5, and 2 times 2 is 4, is greater than 3. Now 1 is less than 5 is true, and 4 is greater than 3 is true. I have to have both of those statements as true statements for that number 2 that I plugged in to be a solution. We do have that, so the number 2 is a solution. Let's try 6. 6 minus 1 is less than 5, and 2 times 6 is greater than 3. So I get 5 is less than 5, and 12 is greater than 3. Now 5 is not less than 5. 12 is greater than 3, but I have to have both statements true since this is an AND compound inequality. Therefore, I know that x being 6 is not a solution. Let's try this OR inequality. First we put in the negative 5. Negative 5 plus 1 is less than equal to negative 4, or negative 5 plus 1 is greater than equal to 4. So negative 5 plus 1 is negative 4, is less than equal to negative 4, or negative 5 plus 1 is negative 4 greater than equal to 4. This is a true statement because we have the equal to part. Negative 4 greater than equal to 4 is not true, but at least this or this is true, so that makes negative 5 a viable solution. Let's try x equals 2. 2 plus 1 is less than equal to negative 4, or 2 plus 1 is greater than equal to 4. 3 is less than equal to negative 4, or 3 is greater than equal to 4. Here, 3 is not less than negative 4. Also, 3 is not greater than 4. Now I know that 3 is not less than equal to negative 4. Also, 3 is not greater than or equal to 4. I have to have at least one of the things true in an OR statement for that number to be a solution, so I know that x equals 2 is not a viable solution. Now let's solve the compound inequality. We'll graph the solution set on the number line and write the answer in interval notation. Here we just need to solve the two individual inequalities, keeping the AND between them, and then I'll place my numbers on the number line in the order that they actually appear on the number line. Even though negative 2 is on the right, it's on the left of 5 halves on the number line. Let's go ahead and test each interval. If I tested a number over here, maybe a negative 3, I could put that in here. Negative 3 is less than 5 halves. That is true. Is negative 3 greater than negative 2? No, it's not. And with an AND, I have to have this and this true. So I cannot shade this interval. Any number that I pick out of this interval will behave the same way, whether it be the negative 3 that I picked or a negative 10. Now let's pick a number in this interval to test. We could test the number 0. Is 0 less than 5 halves? Yes, it is. And is 0 greater than negative 2? Yes. So I know that I have two truths, and I'll be able to shade that interval as a solution. Let's pick a number over here to test. Maybe a 3. 3 is less than 5 halves? That's not true. And because I know that I already have one false statement right off the bat, I know that I cannot shade that interval. So that leaves me with this interval, and let's take care of our endpoints. On the 5 halves, it's strictly less than, so that means we're going to have a parenthesis. On the negative 2, we have a strictly greater than, so we're going to have another parenthesis. Now it's easy to see in interval notation what our solution set will be. Now with this problem, we're already solved. We just need to get it into interval notation. So let's place our numbers on the number line, again in the order that they appear on the number line. And let's test each interval. If I test a number over here, maybe a negative 2, is negative 2 less than or equal to negative 1? Yes. And since it's an OR, I just need at least one of those statements to be true. So I know that I'll shade that interval and keep shading to the left. Let's test a 0. 0 is less than or equal to negative 1. That's not true. Is 0 greater than 2? No. And I have to have at least one of those statements true with that number, so I know I cannot shade that interval. Let's try a 3. Is 3 less than or equal to negative 1? No. Is 3 greater than or equal to 2? Yes. So I have at least one statement true. That means I can shade that interval. Now let's take care of the endpoints. We have the equal to part on both of those inequalities, so I will use a square bracket showing that 2 is included as a solution and negative 1 is also included as a solution. When I write my interval notation, it will be negative infinity to negative 1 with a square bracket, union, 2 to infinity, with parentheses on both of my infinities as usual. We'll have a little bit of solving to do on this one. First, let's subtract 5 from both sides. Then we need to divide by negative 1. Remember, when we multiply or divide by a negative, we have to flip our inequality sign. Here we need to subtract 3 from both sides. So I end up with the compound inequality x is less than 4 or x is greater than or equal to negative 4. Now let's graph and test our intervals. Let's test over here a negative 5. Negative 5 is less than 4. That's true, and since we have an OR, we just have to have at least one of those intervals true. So I'm going to shade that all the way to the left. Let's try a 0. Is 0 less than 4? Yes, it is. So again, I can shade this interval. How about a 5? Is 5 less than 4? No. Is 5 greater than or equal to negative 4? Yes, it is. So I have at least one true thing. I can shade that interval. That gives me a solution set of negative infinity to infinity, all real numbers in interval notation. Again, let's solve here. We add 3 to both sides. We subtract 5 from both sides. And let's place our numbers on the number line in the order that they appear. Now when I'm working on this number line, let's test this interval, negative 7. Is negative 7 less than or equal to 7? Yes. Is negative 7 greater than or equal to negative 6? No. With an AND, I must have both of those true, and I only have one true, so I'm not going to shade that interval. Let's say I want to test a 0. 0 is less than or equal to 7. That's true. And 0 is greater than or equal to negative 6. That's also true. So I'll go ahead and shade that interval. Let's test over here an 8. 8 is less than or equal to 7. That's not true. So I know already with an and they have to both be true. I already have one false, so I'm not going to shade that interval. With my endpoints, both are included, so they get square brackets. My interval notation is negative 6 with a square bracket to 7 with a square bracket. Again, let's solve here. I'm going to subtract 1 from both sides. When I divide by negative 7, that flips my inequality. Over here, I'll subtract 1 and divide by 3. Now when I put these on the number line, I put the negative 10/3 to the left and the 7 to the right. And let's test our intervals. Over here, let's say I test a negative 5. Negative 5 is greater than 7 is not true. And since I have an and, I know I won't be able to shade that interval. Let's test a 0. A 0 is greater than 7. That's not true. So I can't shade that interval. Let's try an 8. 8 is greater than 7 is true. And 8 is less than or equal to negative 10/3 is false. So I have a true and a false. I have to have both true in order to shade that interval. There are no numbers here that I can shade. So the answer here is simply no solution. In other words, there are no numbers on the real number line that are bigger than 7 and smaller than negative 10/3 at the same time. This is a three-part inequality. We can keep these all together when we're solving them. Since we have three parts, think about this. If I had just this inequality, t plus 4 is less than 5, you would know to subtract 4 from both sides. If I had just this inequality, again, you would subtract 4 from both sides. So what I'm going to do is subtract 4 from all three parts. The left, the middle, and the right. When I do that, I get a negative 6 less than or equal to t less than 1. Now let's place those numbers on the number line and read this inequality. T, or the thing that we want to shade, is literally between negative 6 and 1. So I'm going to shade between negative 6 and 1 on the number line. The 1 gets a rounded parenthesis, and the 6 gets a square bracket. In interval notation, it's negative 6 with a square bracket, comma, 1 with a parenthesis. Let's solve here. Subtracting 4 from both sides, I get x is greater than or equal to negative 6. And subtracting 4 from both sides here, I get x is less than 1. I'll place these numbers on the number line and start testing my intervals. Let's say I test over here a negative 7. Negative 7 is greater than or equal to negative 6. That's not true. So I won't be able to shade this because with the and, I have to have both true in order to shade. Let's test a 0. 0 is greater than or equal to negative 6. That's true. 0 is less than 1 is true. So I can shade this interval. Let's test a 2. Is 2 greater than or equal to negative 6? Yes. Is 2 less than 1? No. So I won't be able to shade this interval because the and says I need both to be true in order to shade. So I place my symbols on my endpoints and I'm ready to put it into interval notation. -6 with the bracket, comma 1 with the parenthesis. Now I want to call to your attention the similarity between this problem and the previous problem. You notice that we end up with the same solution set. Remember at the beginning of the lecture that I had mentioned this three-part inequality is equivalent to a two-part inequality that has the and between them. If you look at the three-part inequality, it's saying that t is less than 1 at the same time that t is greater than equal to -6. This is the same as saying x is less than 1 and x is greater than equal to -6. With this inequality, we can go ahead and keep it again as a three-part inequality. When we divide by -2 or multiply by a -half, you'll just need to remember to flip that inequality sign. So I'm going to multiply this by a -1/2. I get -1/4. Greater than, because I have multiplied by a negative. -1/2 times -2 cancels out and I'm left with just the y. Greater than, equal to, and 8 times a -half is -4. Take this whole expression and turn it backwards. Because we're having to read this backwards, it is a little bit confusing when we have to go to graph. -4 is to the left of -1/4 on the number line. So picking that up just like it was written on a piece of plexiglass and turning it over helps us to not have to read the inequality backwards this way. So now I have y is literally between -4 and -1/4. So I'll shade between those numbers. The -1/4 gets a parenthesis and the -4 gets the square bracket. So I have a -4, comma, -1/4 with a bracket on the -4, a parenthesis on the -1/4 as my answer. Now here I have fractions that I can clear by multiplying by 4. If I multiply this fraction by 4, I'll have a -10 less than equal to 2 minus m less than equal to 4 times 1/2 is a 2. Now I need to subtract 2 from all three parts. So I have a -12 less than equal to -m less than equal to 0. Now I need to divide by -1, so that gives me a 12 greater than equal to m greater than equal to 0. And again, this is backwards. So I'm going to pick it up and turn it all around just like it was on plexiglass. And then I have this 0 and 12 on the number line, and m, the thing that I want to shade, is between 0 and 12. They both get square brackets, so my interval notation is 0 to 12, square brackets on both 0 and 12. That covers this lesson. Go ahead and try your homework, and be sure to let me know if you have any questions.